Recall that sometimes knowledge of one event changes our opinion about another event, and sometimes knowledge of one event doesn't change our opinion about another event. If it doesn't, then we say the events are independent. Now, if we have random variables, which are just notation for the outcomes of experiments, it might be that the outcome of one experiment changes our opinion about what the outcome of the other experiment might be, and sometimes it doesn't. If it doesn't, we call the random variables independent. Now you might say, don't we know that already? And the answer is, well, yes, but when we said it before, we didn't use the language of random variables. So let's go over independence again using the words random variables and see what it looks like in this case. So let's recall that events A and B are called independent if knowledge of one does not change our opinion about the other. Now there's three ways to write this that are pretty much equivalent. So A and B are independent if any one of these. Probability of A given B is just probability of A. Probability of B given A is just probability of B. Or probability of A and B happening is just probability of A times probability of B. They're pretty much equivalent. The first two, well, the first one only makes sense if probability of B is non-zero. Because probability of A given B is probability of both divided by probability of B. So this doesn't even make sense unless we know probability of B is non-zero. And this one assumes, similarly, probability of A is not zero. This one is true even if probability of A is 0 or probability of B is 0. Because we don't worry about dividing by 0 here, there's no division. So this one is maybe the best definition out of the three just because it'll work even if we have probabilities equal to 0. Alright, now let's let x and y be random variables. So that is their outcomes of experiments. So sometimes knowledge of one outcome does not change our opinion of the other. So we could say the probability that y equals some value little y, given that x equals some value little x, is just the probability that y equals little y. Or we could say that the probability of x being equal to little x, given that capital Y is equal to little y, is just probability of x being equal to little x. Or we could say that the probability of x being little x and y being little y is just the product of the two probabilities. So if these are true for all values little x and little y, then we call x and y independent random variables. again, technically the third definition is the best, because this conditional probability makes sense as long as the probability that capital X equals little x is non-zero. If that's zero, then this conditional probability is not defined. Similarly, for the second probability, this makes sense only if the probability that capital Y equals little y is non-zero. But for the third equation, multiplying by 0 is never a problem, so that one holds all the time. So this definition is slightly better. So let's look at an example of a pair of random variables that are independent and then a pair that are not. And again, we've already done this, but let's just do it with the notation of random variables. So let's say we roll a 6-sided die n times, and let's let xi be the result of the ith roll. Then if we look at two different trials, we have that the probability that the ith trial is 2, given that the, actually I'll do the product version. The probability that the ith trial is 2 and the jth trial is 3 is just the probability that the ith trial is 2 and times the probability that the jth trial is 3. So knowledge about what happened on one roll of the die doesn't influence our opinion about what happened on another roll of the die. So this is, of course, 1/6 times 1/6, 1/36. All right, now let's choose marbles from an urn. So we'll choose a marble from an urn containing, let's say, 4 blue and 5 white. Let's perform several trials without replacement. So once we take the marble out, it's gone. And let's let xi be the color chosen on the ith trial. So let's look at whether x1 and x2 are independent or not. We can kind of see immediately that they're not, because knowledge about which color was chosen on the first trial is going to influence our opinion about what happens on the other trial. What are probability that x2 is blue, given that x1 is white, and just probability that x2 equals blue? Well, the first one is pretty easy to compute. The probability that x2 is blue, given that x1 is white, is, alright, we remove one white, and then we've got 4 blue and 4 white left. So it's 1/2. 4/8 is 1/2. Now the probability of just x2 being blue is, well, sort of hard to see like that, but if we write this as the probability that x2 is blue, or let's write the probability that x1 is white and x2 is blue, plus the probability that x1 is blue and x2 is blue. So that together makes the probability that x2 is blue. Then we can write this as probability that x1 is white, probability x2 is blue, given that x1 is white, plus probability that x1 is blue times probability that x2 is blue, given x1 is blue. The first one is white is 5/9 times probability x2 is blue given x1 is white. We just computed that, it's 1/2. Plus the probability that x1 is blue, which is 4/9 times the probability x2 is blue given x1 is blue. If we take one blue one out, then there's 3 blue left out of 8. So this is 5/18 plus 3/18, which is 8/18. Divide top and bottom by 2, and we get 4/9. So it looks like the probability that x2 equals blue is not the same as the conditional probability that it's blue given x1 is white. So that means that x1 and x2 are not independent. And that's usually how it goes when we choose things with no replacement. The end.